Okay, I think we'll get started. So today we're going to continue our discussion from last time and look at the motion caused by spring force. And we know that motion is oscillatory because the restoring force action of the spring. If we move this way, the force wants to go that way. If we move this way from equilibrium, the force wants to go that way. So let's look at this. If I take this spring and I'm going to move it, I'm going to pull it back a distance A. And that's called the amplitude of this motion. So I'm going to pull it back to distance A, and that's going to require a force equal to minus Ka. Well, I would have to supply a force of Ka, and then the restoring force here would be minus Ka. I'm going to take a particular, what's called initial condition here. I'm going to hold this, and now I'm going at time equals 0. I'm going to let go, and we're going to watch what happens to this motion. So as I let go, the mass is going to want to move this way, and as it does so, it will start to accelerate. It will lose potential energy, pick up kinetic energy, and as it goes through the equilibrium point, we will have no force on it. It will be moving at its maximum velocity because it's been accelerating that whole time, and we'll have the maximum kinetic energy and no potential energy. Now, as it starts to pass through here, it will experience an opposing force, so that will decelerate the mass, and it'll keep decelerating until it stops at minus A. And that's called its turning point. It will stop and turn around. And then it will accelerate back through, losing potential energy, gaining kinetic energy, losing position, negative position in this case, gaining velocity, and it will pass through this point with the same kinetic energy it had, 0 potential energy, and the velocity will be equal, but in the opposite direction. And then it will decelerate through this stretch until it hits A, right where I let it go, and that's the turning point on this side. So these are referred to as turning points. At the turning point, there's no motion, it stops, so the kinetic energy is 0. We're at maximum stretch or compression, so potential energy is 0. And then the opposite is true at equilibrium, where potential energy is 0, maximum potential kinetic energy. Now, we're going to pursue the rest of the motion based on this starting point, but keep in mind that that is just one possible initial condition. I could have pushed the spring here, held it here, and then let go, or I could have hit the spring with a hammer, or anything in between. So we'll come back and catch that at the end. But now, for now, let's just look at the simple case of a displacement and then a release at time equals 0. So let's plot the position now. Let's capture what we just said in words. And as it turns out, if we work out Newton's laws, which would require some differential equations, we will come up with the solution that the motion is cosinusoidal. So it's got an amplitude of A, cosine, and then omega is the particular circular frequency associated with this. It's related to the spring parameters K and M as the square root of K over M. So omega is a constant of the harmonic oscillator, but it's not a new parameter. There's still just the two parameters, M and K, but oftentimes omega is convenient to use as it is here in this formula. The linear frequency through which it will be going back and forth is just omega divided by 2 pi. And then the period is 1 over the frequency. And the period then would be the time it takes. Oh, this is time here. The time it takes to get back to the original turning point where I dropped it. Okay. All right. Well, if we want to characterize the position, we also want to characterize the velocity and the acceleration. So if you've had some calculus, you'll see this very easily. If you haven't had calculus, I'll just give the formulas here, and you can kind of see where they're coming from physically. You want to develop your physical intuition. So from calculus, the velocity is the derivative of the position, and the derivative of the cosine is negative sine. So we're going to get a minus sinusoidal behavior. Frequency will be the same. Now, why minus? Because my velocity will be in this direction to start with. And it will also be 0. The moment I let go, it's 0. So that's why we've got the sine function. So it's 0, and then it is negative. Velocity here, this is where we're at equilibrium. So again, this is time. I didn't label my axes here. Here's equilibrium position. This is the time at which we're passing the equilibrium point. And then here is the time we are at the turning point. And then here, back at the equilibrium position, now heading in the other direction. And then turning point. And so this is one period. I didn't draw this great, but this is the same amount of time as that. So they're coordinated together. All right, acceleration, again, is the derivative of the velocity. So if you've seen some calculus, you'll see this readily. But this becomes cosinusoidal, but the negative sign persists. Why is that? Because as I let go, the acceleration is in this direction, the negative direction. And again, the period is the same, so the frequencies are locked together here for position, velocity, and acceleration. Let me just pick up something from the last video. We talked about we can get the potential energy as the integral of the force. So force minus kx, and the potential energy is the integral of that, negative integral of that. And so the potential energy is a parabola. 0 potential energy when we're at the equilibrium position, maximum potential energy when we're at the turning points. So at wherever I decided to let go, that's the amount of potential energy in the system. So if I pulled it back further, I'd climb up this curve more. Well, let's put that together with total energy. So we know total energy is kinetic energy plus potential energy. We also know that total energy is conserved as long as we don't have any kind of friction here, and we're not talking about any friction, so this will just go forever. So that should be constant, but it certainly doesn't look like it's constant because we've got all these sines and cosines. But let's work it out. So kinetic energy, 1/2 mv squared. The potential energy, 1/2 kx squared. Well, I know my v's and my x's now from over here. So I'll square the v, that's this part here. This is v squared. And then I'll square the x, that's x squared. Do a little simplification here. This omega, right, that's going to be omega squared, which is going to be k over m, because omega is the square root of k over m. we've got an m up here, so the m's will cancel and leave just the k. So that's where this k came from. The a is just coming along for the ride. But notice now, the prefactor on both of these is the same, so I can factor that out, which happens here. And then I'm left with sine squared plus cosine squared, which, if we remember from trig in high school, that's just 1. And so this whole thing does indeed go to 1. And we've got a constant that depends only on the spring constant and the displacement. And it's precisely this value here. Because I imagine plugging a in for x, and I get 1/2 ka squared. So let's plot that. That's going to be just a straight line in black here. And then let's plot each of the individual terms. So this term and this term. Well, the kinetic energy is sine squared, so that's in red here. And the potential energy is in blue. And so that looks like that. Now, let's put this on this graph here. So let's redraw this graph over here. We'll have energy in this direction. So this is E total. This is our, actually, let me put that in blue because that's potential energy. And then by conservation of energy, if this is potential energy at any point here, that's potential energy. And so this is kinetic energy. So if I were to plot that in red, that's going to look like this. All right. So there's our description of simple harmonic motion. We'll go to a more abstract description, but one that I think is helpful in the next video, and that is the coordinate space description. And this actually lays the foundation for a later course, probably a bit later, depending on where you're at after you come out of these 3 introductory courses on classical mechanics. And so it'll sort of be the seeds of the type of way one likes to picture things, thinking about mechanics in a more advanced way.